Hi everyone, welcome back. So last time we went over that type 4 analysis for our airfoil, where we varied our Reynolds number while keeping the angle of attack constant. And our hope with that was to figure out the kind of critical Reynolds number below which our performance really drops off because we have a lot of separation, and above which we have a boundary layer staying attached, and so we get better lift and drag performance. Now, having done that, what I really want to jump into this time is to focus on what flaps do to the overall performance of our airfoil. So I already ran an analysis for this airfoil. I went from -10 to +15 angle of attack. And this was for a Reynolds number of 100,000, which from our type 4 analysis is well above that critical Reynolds number, at least for most cases. Now let's go to our polar plots and see what this shows us. So I'm going to right click, show all polars. There it is. And I have my graphs here. Now you might not be seeing the same graphs I am, so let's kind of focus on all of these, and I'll show you how to make them if you don't have them. So go to number 1 first. I'm going to hit 1 and it'll show me one graph. It's just my coefficient of lift versus coefficient of drag plot. If you don't have this, you can just double click. Oh, let me do it from this view. That's interesting. Double click from your all view. Oh, variables. I'm being silly. And you can change it from coefficient lift and coefficient of drag, or coefficient lift to coefficient or to alpha, whatever you need it to be. Okay, back to 1. And it does let me do that. Just double click, it'll show up. I just happen to be in the fonts and background section. Now I have my coefficient of lift versus coefficient of drag curve. And what you can see is for various angles of attack, I can cycle through here and see how it changes. And so there's this range right about here from about -3, -4, all the way up until roughly 7.5 degrees, where my performance is fairly constant. My drag is not changing all that much. My lift is still changing. Now, what happens at around 7.5? Well, we can go and visualize that if we want to. So let's go back to our airfoil plotter and see what's going on around 7.5. And right here, it's perfect. So what's beginning to happen here as we get to 7.5 is we begin to have more separation. So you can see that in this area back here, it's beginning to lift away from the airfoil. And as I go to higher angle of attack, that separation will get more severe. I'm not clicking right there. There we go. You can see it continues to get more and more severe. The more severe that separation gets, the more pressure drag I have, and the worse my performance. So back to the back to the polar plots. Okay, so this is one thing you can be looking at here. Now, one thing you might notice is that there is a point right around, let's see, I think it's around here, where I have a minimal drag coefficient. So around 2 degrees angle of attack, I have this minimal drag coefficient. And a question you might have for yourself is, well, is that where I have the best performance for my plane? Well, let's look at another graph to figure that out. So another graph that can be very, very helpful is to take the glide ratio, which is the coefficient of lift versus coefficient of drag, versus your angle of attack. So we're going to look at that plot right now. I'm going to hit number 3 to bring it over here. And at 2 degrees angle of attack, you can see that my glide ratio is not a maximum. In fact, my maximum glide ratio happens somewhere around, let's see, 7 degrees. So right at that point, right before my separation begins to happen, well, very significantly. So your glide ratio is a better measure of the overall performance of your aircraft, at least how efficient it is running. And when you maximize this, what you find is the point where you have the highest glide ratio is actually the point where you have the minimal total drag force, not the minimal coefficient of drag, but minimal drag force. If I want to be flying at my, in the best situation, I want to be the most efficient for my fuel, then this is the best place to do it because this will require the least amount of thrust. And remember, thrust means I'm running my engine. If I'm running my engine, I am burning fuel. So least thrust means least fuel use. And so for us, for this particular airfoil, we would have the best fuel economy somewhere around an angle of attack of 7 degrees. And there's a lot more that goes into that. I'm oversimplifying some things, but just wanted to show you that detail. Now my question then is, well, how would all these graphs change if I add in a flap? So let's do that right now. We'll go back to our airfoil plotter so we can see our flap. And for once, it's not randomly changing its size, which I greatly appreciate. And let's go ahead and add some flaps to this guy. So I'm going to go ahead and select it. Then I can go to Design, and I can say Set Flap. I'll say F10, but I'm just going to use the toolbar to help me get there. Do we want a leading edge flap or a trailing edge flap? We want a trailing edge flap. And what's the flap angle going to be? I'm just going to pick a number. I'm going to say 7 degrees. As a note, positive is down. If I click Apply, you'll see it goes down. Where's the hinge position and Y position? Well, for that one, 50% of the thickness makes a lot of sense, and 70% of the chord is fine. This is going to be dependent on your geometry. So if you're making an RC plane, well, make it based on how your RC plane works, and go from there. So I'm going to call this one Flap Down 7 degrees. I'm saving it like a new airfoil. Click OK. Now I'm going to do the same thing, but flap up 7 degrees. Okay, so let's go to Design, Set Flap. Actually, let me click on this guy again, make sure it's not going to do anything strange. Design, Set Flap, Trailing Edge Flap, and this time a -7. Click Apply, it's going up like I want it to, and I click OK. I'm going to call this Flap Up 7 degrees. Okay, now that we have these two new airfoils, more or less, I'm going to run an analysis. The same analysis I ran, which is a type 1 analysis at a Reynolds number of 100,000, with all the other settings just at their normal one, their defaults. And so we'll do that for both of these now. I'm going to try to do the same range I did before, which was from -10 to +15 degrees angle of attack. So we go to Analysis. I go to Define Analysis. This all looks fine. Click OK. This is now available to me, so it's already set to negative. I'll just go ahead and run that. Analyze. And my goodness, a lot of data. I'm not worried about getting rid of it yet. Let's go to +15. Analyze. And we're good. So that's too much information for me. That's just blowing my mind. And all the numbers seem to be here. It didn't show me any error for that, so I think we're good for this one. Now let's do it for the flap down. Same thing has to happen, so I go to Analysis, Define Analysis. All that's still good. And I'm going to go up first this time just because it's already set for that. Click Analyze. Now, here is what I wanted you to run into. So this box stayed open. As a note, if it stays open, usually something has gone wrong. So there's a setting you can click on which will make sure this happens. And so it says right here at the bottom that some points are unconverged. If I go up, I can see converged after 4, converged after 4, converged after 57. And there's one right here for 7 degrees angle of attack where it's unconverged after 100 iterations. So it might be good for me to go back and to rerun that, but using a smaller step size. So I'm going to try that. It says 0.5, let's do 0.25, and let's hit Analyze. Some points are unconverged. To have an even harder time, it still really struggled at 7 degrees, which I guess is probably because of the flap angle. Some one struggled too, 5 degrees too that time. Okay, we'll try one more time. And we'll just do something a little bit different. I'm going to go 0.3, see if I can skip that angle that's really giving it trouble, and hit Analyze. Okay, and still somewhere around there, it's struggling. So we're just going to ignore that point right there because that's the only one that's unconverged. The rest did converge. I'm just going to have to leave it for now. A lot of times, though, you can fix things by changing your step size there. I could go in and refine the airfoil if I needed to, but I don't want to take too much more time for this. Okay, that was going in one direction. Now let's go in the other for it. So from 0 to -10. And click Analyze. Beautiful. So all those did fine. So got way too much nonsense on that page. Let's get rid of that. And now we're going to go back to our polar plots. So I already have my regular one. Let's go ahead and show that for the rest. So let's show all polars. Beautiful. And you can see some craziness happening there at the end. So I probably should delete those values, but I'm not going to worry about it too much for now. Actually, I do care. Let's see if we can remove those for now. That'll take too much time. So what we're going to do now is I'm going to go ahead and change those colors just a little bit because they're not very clear, especially on that white background. So we'll click on this one. We'll go for width. I think it'll be better than anything else. There you go. And we'll go for the other one as well for flaps down and change its width to a little bit thicker. Okay. And finally width right here to green. Fantastic. That looks good. Okay. So with this, we can see various things before it goes absolutely bonkers over here at the end. I definitely chose too high of a range of angle attacks, especially with the flaps down. But that's life. So what do we see? Well, first off, we see that when we increase our flaps, so that's the blue line right here. I'll go ahead and zoom in on this. When we increase our flaps, we're automatically increasing our drag. But we're also increasing our max coefficient of lift. Now, on the other side, though, surprisingly enough, when I put flaps up instead, so instead of flaps down where it's increasing lift, flaps up where it's decreasing lift, I actually don't have as much drag increase with that aspect of it. Now let's look at our glide ratios. Another thing you can see is that with flaps down, my ideal glide ratio changes. So my angle attack for my ideal glide ratio changes. So I go from somewhere around 7 degrees to having a maximum somewhere around 4 degrees with the flaps down. And with flaps up, it goes to the right. You also see that my glide ratio increases with the addition of flaps. So there is going to be some optimal angle of attack slash flap deflection to get to you the best performance possible for your aircraft. Okay, with that being said, I've shown you how to do flaps. We've seen how we can see their performance and how that changes for all these. We've seen some fun convergence errors when I went way too far. Beyond that, I think we're good for now. So thank you all for listening. I hope this helps you, and I'll see you all next time. Bye-bye.